speaker is Jelena Diakonikolas. Right now, she's an assistant professor at University of Wisconsin and joined right before the pandemic. So she's had an interesting first year, and she's been doing a lot of really interesting work that I've seen since I met her back in 2017, I think, at Simons Institute, where she was a postdoctoral fellow there, actually Microsoft Research Fellow there as well. And after the Simons, she did a brief postdoc with Michael Jordan for about a year or so, and joined the computer science department at University of Wisconsin. And so today, Jelena is going to talk about min-max optimization and some of the inherent structure that we can use to tackle this difficult problem.
Thank you very much, Damek. It's a pleasure to be here. And as Damek said, feel free to interrupt me. I sometimes tend to get really excited about this stuff and start talking too fast. So if that happens, also feel free to tell me to slow down or if I need to explain anything again. So what I wanted to talk about today is min-max optimization and some things I found surprising about it, and perhaps some interesting ideas. I mean, you'll tell me if they're interesting or not. So our setup for the talk is that we have a min-max optimization problem. There is a function f that we want to minimize over x and maximize over y. These x and y's are constrained, and the constrained sets will here be closed convex sets. Sometimes in the talk, and actually for most of the talk, I will be assuming that this function f is convex-concave, which means convex in x if we fix y and concave in y if we fix x. And one of the most basic results that started the whole area is the minimax theorem due to von Neumann, which tells us that when f is convex-concave, and if these two feasible sets are convex and compact, then a solution to this problem exists, and we can exchange the order of min and max. Now, there are some generalizations to this minimax theorem, as many people here will know, but in full generality, once we remove the assumption that f is convex-concave, it does not hold in general. Min and max may be different, and even guaranteeing that a solution exists is a whole research area. Nevertheless, we do care also about the setups where f is convex-concave. It's a central result in game theory. Von Neumann himself said that game theory wouldn't make sense if this result didn't exist. And it's also central for optimization. The setups where we don't have f be convex-concave are also setups we care about. People have cared about it for decades, but more recently it has come into focus because of some applications in machine learning, particularly in adversarial training, but also there are some instances of reinforcement learning that problems like this come up. Okay, so obviously, unless we have very special problems, we would never be solving them exactly. So we need to talk about what kind of guarantees we can give for the problems. And there are normally two types of guarantees we look into. So if we had a candidate solution and some target error epsilon, one type of guarantee would be in terms of the optimality gap. And this normally makes sense when the function is convex-concave. And, you know, it's a standard notion of optimality gap, how much you can improve over y if from your candidate solution, and how much you can improve over x from your candidate solution. This shouldn't be larger than epsilon. If epsilon was 0, you know, this would be the optimal solution. Another type of guarantee is in terms of stationarity. If this doesn't make sense, just note, it's just a generalization of what you would write for standard optimization. You're just accounting that you have min and max part. And if you were in the unconstrained regime, this would boil down to have a gradient that is at most epsilon. And it suffices for this talk to just think about that setup. Now, one thing I want to get out of the way immediately is that standard optimization is different from min-max optimization. And I want to emphasize this because I very often see papers where this seems to be forgotten, because it is quite tempting to work with what you're more familiar with and try to kind of reduce things to standard optimization. But let me give you just a couple of examples. So let's look at a setup where, in standard optimization, we have a function that is convex and L smooth and has a minimizer. The corresponding setup for min-max optimization would be that the function is convex-concave, L smooth, and has a min-max point. For the standard optimization, we have that the optimality gap is going to be finite. So let's say, our space is RD. For min-max optimization, if you remove this assumption of compactness, the gap could be infinite as soon as you move away from the solution. So even though a solution exists, if you just move away a little bit from it, you get an infinite gap, where I have defined the gap in the previous slide. And an example is just x times y. And I'll go through this example a little bit more later. Another thing here is that, one of your most basic methods, which is gradient descent, in standard optimization, it converges. For min-max optimization, the appropriate generalization would be gradient descent ascent, and it diverges in general. This is a well-known result. Now, things become even more interesting when you start looking into non-convex setups. So for non-convex smooth functions, if a minimizer exists, or even if the function is just bounded below, we know that gradient descent would be converging to, let's say, a point with a small gradient, to a point with gradient to epsilon in poly 1 over epsilon time, so computationally tractable. You look at the counterpart setup for min-max optimization, and the problem becomes computationally intractable. In particular, the problem is what is known as PPAD complete. It's a complexity class similar to NP complete. All problems polynomial time reducible to each other. No polynomial time algorithms exist. So this is just for getting a gradient of value at most epsilon. And if you look at oracle-based algorithms, like first-order methods, the complexity is exponential in at least one of the parameters, at least either the Lipschitz constant or 1 over epsilon or the dimension. So very, very different things, even in these like very, very basic setups. Okay, so my plan for this talk is that for the first setup, where I said, the gradient descent doesn't make that much sense and the optimality gap could be infinite, I will talk about an algorithm for approximating a stationary point, which in the unconstrained setup would be for making the gradient small, and what is the complexity of this problem and what kind of algorithms work. I will spend a short amount of time also talking about non-convex-nonconcave optimization problems, because in full generality, they are intractable. Here, we need some structure. So I'll talk about one type of structured problems that we can consider and what kind of results we can get. And then at the very end of the talk, because I don't want to end up on a negative note and give an impression, these problems are just more difficult, we always need something extra, I'll talk about a setup where we have a convex optimization problem, but the min-max perspective turns out to be useful in the sense that we can actually get a faster algorithm, and this will be a specific setting will be variance reduction for empirical risk minimization problems. Okay, so this is the plan. And as I move between these different results, you'll see a slide that looks like this. And it will give a reference to the paper I'm talking about. And if you scan the QR code, it will take you to the paper. But this result is what I'll spend most time in, because I wanted to take a little bit of a deep dive here. Okay, so the setup here is we have a function that is convex, concave, and smooth. These problems are very often considered through certain abstractions. And those abstractions, in these abstractions, we work with the monotone operators. So an operator is monotone if it satisfies something like this. So this type of relationship holds for gradients of convex functions. But also if you have a convex-concave function and you stack the gradient with respect to the convex part and the negative gradient with respect to the concave part, you get that the resulting operator will also be monotone. Now, for monotone operators, there is lots of literature on different types of problems that people look at. One of them are variational inequalities, for which there are two main types of problems known as Minty variational inequalities and Stepakia variational inequalities. Their corresponding solutions are known as weak and strong. Now you look at this, and they kind of look the same, right? Especially if you're not paying attention. The difference is here f is evaluated at u star, which would be your solution. Here it is evaluated at the arbitrary u. Seems like a small difference. Typically, it's easier to approximate these problems than it is to approximate these problems. Another type of abstraction that people consider is known as monotone inclusion, where you want to find the zero belongs to f of u star plus this weird thing is the subdifferential of the indicator function of the constraint set. If it doesn't make sense, the bottom line is, if you were in the unconstrained setup, you would be looking for the zero of this operator, which would be the same as looking for the zero of the gradient. All this thing does is just account for the cases where you would have a constrained feasible set. Okay. Okay, so if all of this doesn't make sense, I'll still tell you some things that will hopefully make sense, but you don't need to memorize all of this. It's more for people who are familiar with this stuff. So
can I
yes.
ask one quick question? I see that the Stepakia strong solution says basically that the f is the normal vector of u at u star. But the Minty VI, the weak solution, I don't really have a good sense of what that is saying, like geometrically, or like why one would consider that to be some sort of solution.
Oh, good question. And the reason is all of these solutions are actually equivalent in the convex-concave setup. This is just a kind of a relaxation, and one of them implies the other just by monotonicity.
But in the
so if you
oh, in the non-convex non-concave setup, it would
so let me see. So if so if this was a gradient of a function, and you were in the vicinity of the of a local minimum, this would give you an upper bound on the optimality gap. This would kind of give you a lower bound, but you would hope that they're kind of close to each other.
Okay. Okay. Yeah, because I can see the Minty one. I mean, it says weak, but it's definitely weaker.
Yeah. So
lower thing. Okay.
Yeah, I'll mention a little bit more about this. The variational inequalities, interestingly, people didn't start looking into them because of min-max optimization or optimization at all. They came from some equilibrium problems in dynamical systems. But yeah, I don't know how Minty came up with this originally. Maybe someone here will know more about it. Yeah. But so if you look at now what kind of guarantees you're getting here, if you approximated these problems and wanted to translate it back to your minimax function, these will give you normally guarantees in terms of the optimality gap. The monotone inclusion will give you guarantees in terms of stationarity, which would be a small gradient in the unconstrained case. Now, one of the most basic facts, if you look at these three types of problems, is known as Minty's theorem, and it tells us if we have a monotone operator, then it doesn't matter which one of these problems you're solving, all of these solution sets are exactly the same. So what's the point? Like, why even bother and look at different things? Well, we almost never solve any of these to zero error. So once you start looking into approximate solutions, things look different. And by approximate solutions, I mean you add some margin epsilon. So this B of epsilon is just a ball of radius epsilon. It's exactly, if you were unconstrained setup, it would mean your gradient is at most epsilon. And you do a similar thing for variational inequalities. You know, instead of 0, you put epsilon, which would be your margin. Now things become really interesting, because if you had an unbounded feasible set, so just unconstrained setup, let's say, then doing this stuff is completely meaningless. You really need compactness for something like this. So what I mean by that is just take a simple example that I mentioned before, just x times y. This will be your monotone operator. And then, you know, the minimax point for this function is, and also a solution to these variational inequalities is just 0, 0. Take any point that's not 0, 0. The thing on the left is your strong solution guarantee. By monotonicity is going to be greater than or equal to this, which would be your weak solution guarantee. Plug in what this f is, simplify, this is what you get. So if you're not at 0, 0, because I'm taking x and y to be from R, when you take sup, this is going to be infinite. Right, so it just doesn't make sense. Another thing that happens here that is interesting is even if you are in the constraint setup, this is what your solution sets will look like. So the set of approximate weak VI solutions, or these Minty solutions, is the largest one. It will contain all of the approximate strong VI solutions, and this will contain all the epsilon over d approximate solutions to monotone inclusion. So if you're solving monotone inclusion, you're immediately getting guarantees also for strong and weak VI solutions. And this was kind of one of the reasons why I was particularly interested in monotone inclusion, and the work I'll talk about is specifically for that, but you can think about it as just making the gradient small. Now, before I start telling you more about technical parts here, let me just mention some history bits here. So minimax optimization, as far as I know, and I hope I'm not wrong here, was originally studied within game theory and economics. And the first questions asked there were about the existence of solutions. Variational inequalities, they started with something known as Signorini problem and have been studied since the 1960s or so. And these were equilibrium problems. So completely separate, you know, from game theory and optimization. But very early on, people have realized these connections, and when they were coming up with the algorithms, they would just attack both problems at the same time because they could. And in terms of algorithms, their results since at least 1970s, there were results for asymptotic convergence in terms of the points, like distance to opt. There were already rate guarantees even since 1970s, at least for some structured bilinear problems or strongly monotone problems. In terms of rates for just general problems, which would be like smooth minimax without strongly convex-concave. In terms of rates, I think some of the earliest results are like due to Nemirovsky and Nesterov, and there is a whole line of work that has followed. For strong solutions, when it comes to rates, at least, there was much less. And I knew maybe about a couple of results that would be like your standard first order methods. And more recently now, there has also been work on some structured non-monotone settings, which would be structured non-convex, non-concave settings. There's a whole line of assumptions, and I'll talk more about this later. At least I'll give a brief overview. Okay, so for this part of the talk, if you don't want to think about, variational inequalities, monotone inclusion, this is way too much terminology. The basic problem is I have an operator that is monotone, it corresponds to the gradient, and I want to find a point that has the small norm of this operator, some epsilon. And again, as a reminder here, I'm assuming that my function is convex-concave, which means that this capital F is monotone. Now, this thing, as I said, is well defined even when approximating the optimality gap is not. And in general, even if approximating optimality gap is well defined, if you get an optimal rate for this problem, it implies the optimal rate for minimizing the optimality gap. What is your guess for the opposite direction? Any guesses? Or maybe someone knows? Another 2 seconds. Okay, then looks like no one wants to guess. The opposite direction does not hold. There is a paper, I'm oversimplifying what I'm saying here, but informally, if you look at a bunch of these different methods that give you the optimal rate for making the optimality gap small, so smooth convex concave setup, and your favorite method, Extragradient, mirror prox, Popov's method, dual extrapolation, they have the optimal 1/k rate for reducing the optimality gap. Their rate is no faster than 1/√k, and this holds for actually a broader class of methods that just encapsulates all of these methods. So yeah, this is definitely something that is more general. So the standard methods we've had for that we typically attack min-max problems with are out. So what can we do? Clearly these are not the right methods to look into. So we need to think in a different direction. And that different direction is by looking at a different connection between this problem and something else. Now that is what I'll call structure here. And it is actually just a very well-known fact that if I had an operator that is something known as cocoercive, then up to a linear transformation, it is equivalent to a non-expansive map. So I have that this F is 1/L cocoercive if and only if T is identity map minus 2/LF is non-expansive. It doesn't expand distances. It's not necessarily contract. Now, here I'm making a bit of a stronger assumption. So cocoercive implies that the operator is monotone in Lipschitz. The opposite direction does not hold in general. However, it turns out that it is sufficient for me to understand, well, this case to be able to tackle also other standard classes of problems. But this fact that I'm not even sure who to attribute it to, it's in textbooks, is kind of the core of everything that will follow, that I'll talk about. So let me tell you what kind of results we can get, and then I'll tell you a little bit more about the algorithm and the ideas. So first of all, the problem classes that I have looked into are determined by the assumptions I make about this F. The first problem class is when F is cocoercive, and it's this assumption. So if it was just monotone, you would have 0 here. So we're assuming something more. It implies that this is Lipschitz. You can take just Cauchy-Schwarz on the left-hand side. And the norms for this part are just Euclidean norms. Okay, so the second class would be monotone and L Lipschitz. I assume everyone here knows what L Lipschitz is. And the third class would be if the operator is L Lipschitz and M coercive or strongly monotone, where now here I have some factor M times the distance between U and V squared. Compared to cocoercive, note that here it's F of U minus F of V, here it's U minus V. Seems like a minor difference, but this is generally a stronger assumption. Okay. And I'm not interested in any type of method here. I would like to have a method that can work without the knowledge of these parameters. Okay, so those methods are known as parameter-free. So I'll throw the results at you. This is a huge and intimidating table until I tell you just how to read it. So there are 3 large columns for 3 problem classes. So first is for cocoercive setups, the second for Lipschitz and monotone, and the third for Lipschitz and strongly monotone. Each column has 3 subcolumns for the 3 types of solutions. So weak VI, strong VI, monotone inclusion. These are the results from my paper. These are the best known. The green color indicates that the method is parameter free. The red that it is not, that you need to know the parameters. Okay, and then the notation is kind of standard. So for the cocoercive setup, the results I got pretty much match what was there in the literature, but it's the first result where you get a parameter-free method for strong VI monotone inclusion. For Lipschitz and monotone, this O tilde is hiding a log 1 over epsilon factor. So it is off by log 1 over epsilon in the weak VI case. For strong VI monotone inclusion, not only is it parameter-free, where we did not have parameter-free methods, but you actually get a better dependence on epsilon and the diameter of the set. So it's like a quadratic improvement. For the third class of problems, there is also a log factor that is off. So here it would be log L over M. But as far as I know, this is the only result that is parameter-free. These all would need to know at least M, the strong coercivity parameter, the strong monotonicity parameter. Okay, so let me tell you a little bit about how these results were obtained. So the main idea here is to actually use a method for solving fixed point equations with non-expansive maps. And the method I looked at is known as Halpern iteration. It's a very old method from 1967. What you do in this method is you take a convex combination of the initial point and the map of the previous point. These lambdas are step sizes. They're typically of the order 1 over k. And for this method, there was a recent result that actually gave a convergence rate even with a very nice constant. Okay, so going back to the structure that I mentioned, what does this have to do with making f small? Well, you know, if I had a cocoercive operator, then I know that this one would be non-expansive. And if I look at that map that is, you know, identity minus 2 over LF, what will be the fixed point of this T? What does that tell me about F? So fixed point is where T of U equals U. So what happens for F for this specific choice?
It's a 0.
Exactly, it's 0. And also, like, if this is order epsilon, F is also epsilon. So it's like, these are equivalent problems. And this existing result already gives me a convergence rate, which is 1 over k. But I would need to know L to apply it. And then also, I don't know how to directly extend it to other cases. So what was the main idea that, well, maybe before I get to that, let me just state the algorithm. So you know, you use the Halpern algorithm, you just use this equivalent non-expansive map here based on F. So what the main idea here was to come up with a certain potential function argument for analyzing this method. So it gives a different proof. where I maintain a guess for the cocoercivity parameter that my algorithm will be updating. And just as a reminder, this is the step size. I cannot get too much into this, but roughly this potential function, you can think of it as trading off this norm of f with something that would look like an optimality gap. But let's not go into more than that. It's a whole separate discussion to have. So the main argument here is just to show that this is going to be non-positive, for a suitable implementation of the algorithm. Because if you had that, you just rearrange this. It gives you an upper bound on the norm of f squared. You add and subtract u star, which is a solution. Because it is a solution, this is going to be non-positive. You apply Cauchy-Schwarz to this first term. If f was 0, you would have been done. So assume it's non-zero. Cancel out both sides, and you get this. And if your estimate was not too off, and this worked for the choice of step sizes order 1 over k, which is a standard choice of step sizes for Halpern iteration, you get the desired iteration complexity, which is of the order 1 over epsilon, and also turns out to be as good as you can get. Okay, so this is just the unconstrained setup. So for constrained setup, you would do what some of you would guess that you would do, which is use something known as operator mapping, or also natural mapping. If you have seen gradient mapping in convex optimization, it's kind of the same thing. So what it does, it just generalizes a type of gradient step to constrained setups. So if you were to take a step that looks like this, which is similar to a gradient step, if you stayed in the feasible set, gradient mapping would be the same thing as your f. If you stepped outside, then you project back, and this would be this gives you the equivalent step that remains within your feasible set. Just think of it as a generalization of a gradient step. So the reason this is useful is, first of all, when f is cocoercive, then this map is also cocoercive. You need something about the zeta, and you don't know really L. So you need some local variant of this, but that's what's handled by the analysis. The second part is that it suffices to make the norm of this operator mapping small enough to solve your original problem. So it's just a kind of a reduction. And if you do that, you can recover the same iteration complexity. So it's same as for the unconstrained case. Now, so this is one class of problems. If you go to Monotone Lipschitz, there, I don't know how to work directly with f, but what I do know how to work with are the resolvent operators, and many people here are very familiar with them. Again, this was just taking care of the constraints. This is the indicator of the feasible set. If you haven't seen it, it might look scary, but the basic fact about it is that if you have a monotone operator, then the resolvent is non-expansive. It's even a little bit more than expansive, but non-expansive is what suffices for us. And if you find the fixed point of the resolvent, you solve the original problem. And even if you find the fixed point to error epsilon, you get the epsilon approximation of the original problem. So the bottom line is that you could apply known results for Halpern iteration, but those would require you to compute this resolvent exactly. And that's something we know how to do only for some very special problems. In most cases, we don't. So what do we do then? Well, it turns out that even though you cannot really efficiently compute it, you can efficiently approximate it. And what you then need from the analysis is that it works with inexact evaluations of the operator. So that's kind of the main extension that you need here. You lose a little bit. So the cost that you pay for doing this, for approximating the resolvents, is log 1 over epsilon, but it's still not bad. So you just lose the log 1 over epsilon factor compared to the cocoercive setup. But this is where the meat of the analysis happens, just ensuring that things work even when you have inexact evaluations. And now to go from here to Lipschitz and strongly monotone, it's not that difficult. So what you do is you use the previous result plus adaptive restart. So your algorithm is just use the algorithm for the monotone Lipschitz case based on the resolvent, run it until you have this fixed point guarantee, and restart. And when you restart, just use the previous point you constructed. That's the whole algorithm. If you do that, this will be your iteration complexity. This will turn out to be the number of iterations between restarts. This would be the total number of restarts. And this is off by just this log condition number. Now, it turns out you can also certify that all of these results I've shown you are near optimal to up to like log or log square factor. And the way that can be done is based on a known lower bound due to Ouyang and Su, which is for min-max optimization. So the idea is just to leverage this lower bound and do different reductions between problem classes. So if you do that, you can show a lower bound of this order for the monotone Lipschitz case, which means that the algorithm I've shown you is tied up to a log 1 over epsilon factor. For the cocoercive setup, the reduction will lose the log 1 over epsilon here. If you restrict the problem, the algorithm class, you can actually get that this is tight. So that's just in a more recent paper of mine, but ask me about it if you're interested. I'll talk more about it. And you can also get a lower bound for the strongly monotone Lipschitz case. This log 1 over epsilon really shouldn't be here. It should be in the lower bound, but that's just the consequence of the reduction. Okay, so here is the summary of the main ideas. Unconstrained cocoercive setup, you use this connection between cocoercive operators and non-expansive maps. And you handle this case, and to go to constrained setups, you use operator mapping. To go to monotone Lipschitz, you use inexact operator evaluations. And for the strongly monotone Lipschitz setup, you use adaptive restart. And then to certify near optimality, you use all these different lower bound reductions. Now, if I haven't really convinced you from the complexity standpoint why we should care, there is another reason I really like this Halpern iteration. And it's a very well-known result about it that says that if your optimal solution was not unique, you're going to converge to the solution that is closest to your initial point. So here I have constructed a function that has many optimal solutions, everything in this pink rectangle. So wherever you start, you're going to converge to whatever is closest. So the reason this is interesting is if 0 is a meaningful point that you can start from, you would get a minimum norm solution. And okay, my results are for the Euclidean case, but this fact holds for arbitrary norms. So if you apply this for the L1 norm setting, you would be getting sparse solutions. That's really nice. And you don't need to do anything extra for it. It's just the property of the algorithm. Okay, so this was convex-concave setup. Let me now, in the remaining time I have, talk about some other results. And I'll spend like just a few minutes on each. So what happens for the non-convex-nonconcave setup? This is a joint work with Kostis Daskalakis and Mike Jordan. So our goal is the same as before, as in the part I've just talked about, but now I don't have a convex-concave function anymore, and this capital F is not monotone anymore. Okay, so what is known here about hardness? Let me just make things more concrete. If you just work with the non-monotone operators, if you directly work with this F, and you only assume it is Lipschitz, the hardness is something that follows from hardness of finding fixed points of Lipschitz maps. And this was known since the late 80s, early 90s. So this PPAD completeness, exponential lower bounds. Specifically for min-max optimization, because the hardness of F, it means it's hard for min-max optimization only if you can always relate it to a min-max objective. And for that, there is a similar lower bound obtained only recently that assumes compactness of the feasible sets. Compactness here was needed just to certify the existence of a solution. So technically, the unconstrained minimax setup is open, but given these two results, I wouldn't hold my breath. I wouldn't expect them to be any easier. I think it's just you need a better construction of this lower bound. So now just when you think about this, it might be a little bit confusing, especially if you're someone who works with non-convex optimization, because I only want to find a stationary point. So in non-convex optimization, right, you would run gradient descent. Why can't I just run gradient descent here? If my function was bounded below, I would find a stationary point. Or if it was bounded above, I would also find the stationary point with gradient descent. So what's the deal? Why not do that? It's not a reasonable assumption that my function is either bounded below or above. Like the most basic setup where the function is even convex-concave, neither bounded below nor above in general. So it's not something I should be allowed to make as an assumption. Okay, so the most general non-convex, non-concave problems are out of question. I cannot do anything for them, like smooth non-convex, non-concave. So I need some type of structure. And here what I mean by structure is I need to define a new problem class that is subclass of this. So we came up with the condition like this to define this problem class. It makes sense because in special cases, it gives some things people have looked into before. In particular, if this parameter was 0 here, it is equivalent to saying that a weak solution or a minty solution exists. And this is something that was already studied in the literature. And this setup contains things like when the objective function would be pseudo-convex concave, quasi-convex concave, star convex concave. So all these kind of generalized convexity setups. It was also studied another special case was studied and known as a co-monotone setup or co-hypomonotone setup. So this is a special case of this because you recover this condition when you take this V to be a solution, to be just U star. And this was originally studied to explain why proximal point method converged on some non-convex, non-concave problems. It was kind of a surprising fact and people wanted to understand why this happens. So there are results even from 04 on this. There are reasons why this is interesting even without the special cases. So there was a nice problem for reinforcement learning where you can get a problem where extra gradient, which is standard method, works well, but you cannot explain it with any of these conditions. This just gives you kind of a wider class that explains why it works. Okay, I'll just state the result and I won't say much more about it. The algorithm we used here, it looks pretty much like extra gradient. The only difference is extra gradient would take the same step size here. Here we take a slightly shorter step. And if this row is not too large, then you get convergence that is of the order 1 over epsilon squared. And I don't know how to get anything better than that, at least for this condition. And you can also get stochastic variance of this method. It becomes worse. The dependence on epsilon then becomes 1 over epsilon to the 4th. If you're someone who's interested in this problem, ask me about this, because I'm actually quite puzzled by this. I don't know how to get anything better, even for convex-concave setups when it comes to making the gradient small. Okay, so that's all I'll say about this specific problem. So the structure here is introducing a new problem class that kind of makes sense. Now, the last part here is to just tell you briefly about a problem where I don't have a problem that is a min-max optimization problem. It is a convex optimization problem, but looking at it from a min-max perspective turns out to actually be useful. And the work I'll talk about is a very recent work with my postdoc Xiaobing Song and my colleague Steve Wright. So the setup is, you have a finite sum problem. Typically, people consider these in empirical risk minimization, but they'll come up in other places as well. This specific setup where you just write objective like this, and you just take Fi's to be from some standard class like convex Lipschitz or convex smooth or strongly convex and smooth. These are very well studied in the literature, especially recently, and there are tight lower and upper bounds on the iteration complexity of the methods, even assuming that you can compute proximal maps for people who care about proximal point methods. Okay, so if you're just looking at these broad classes, you cannot do better, and we already know what is the best you can do. But empirical risk minimization problems, they're kind of special. So they typically take this form where you have loss plus the regularizer. And this loss tends to be even more structured. It is very often separable. So very often you'll have like these individual loss functions that are functions of, the data row transpose X. But if you have this, then just using the definition of convex conjugates, you can write it as a min-max problem, where this convex conjugate is now just mapping R to R. It's a 1D function. And then this turns out to be quite useful. So you have a bilinear term, these super simple functions, and the regularizer. And for most common problems, you can also compute proximal operators quite efficiently, both for these L star and R. Proximal operators, I'm assuming people know. If you don't, doesn't matter for the whole story. And the examples of this, are your support vector machine, least absolute deviation. So these are for the non-smooth cases, which we mainly handle in this work, but also like smooth setups like lasso, bridge, and so on. Well, lasso, not the regularizer is not smooth, but okay. So let me just tell you what kind of results you can get just from this insight. Well, I mean, there's quite a bit of technical work, but this insight is kind of crucial. If you have that this convex conjugate of the loss and the regularizers are just convex, they could be non-smooth, you get iteration complexity that looks like this. So there is no n here. The constant for this part is 1. So essentially, you pay a little bit more than just reading your data. After that, you get something independent of n. If your regularizer is m strongly convex, if you're using ridge regression, elastic net, or something like that, you can get even better dependence on epsilon. So it goes from 1 over epsilon to 1 over root epsilon. M is the strong convexity parameter. So no dependence on n whatsoever in the second term. And the the number of arithmetic operations per iteration is order d, which is very efficient. And why this is super interesting is if I was not assuming anything about these individual loss functions, if I only took that they were non-smooth and I can compute proximal operators, the lower bound would have root 10 in the second term. So you're essentially saving root 10 factor here. from this separability structure. Okay, so let's get to the summary. I think that many of these min-max optimization problems should be studied separately. You need to think about them differently, but there are many beautiful properties to explore and nice results to get. Sometimes it's necessary to use structure, sometimes it's just plain useful. And I have some open questions for each one of the results I talked about. I'm happy to go into more depth if there are questions, but at this point, I would like to stop and take the questions from the audience. Thank you very much for listening.
Great. All right, thanks so much, Jelena. So I'm going to open it up to any questions. I think I hit that I have a question. I didn't mean to do that. So if anybody has any questions. I think Matteo texted me on a different channel that he has a question.
Okay.
Yeah, I was wondering, why are you considering these different types of convergence? Why are they important?
Different types of convergence in the first part of the talk.
Yes. Yeah.
So there are a few things there. So the one main reason why I thought this was neat was because you can get a parameter-free method for the strongly monotone case, which I don't know how to get without restarts. And the restarts only kind of make sense for the norm of the gradient. The same goes for convex optimization. These type of results normally are for the last iterate, which for some reason I don't understand enough people care about in game theory. I guess they're just also the most general. Now I'm trying to think about a specific case where you would, well, I mean, this notion of convergence also is the only one that makes sense if you have an unconstrained setup, right, from what I said at the beginning. And it's one of the, stationarity is something you also need to understand if you want to go to non-convex-nonconcave setups, because there you cannot really hope to have guarantees in terms of the optimality gap, right? So those would be my main reasons. I don't know if that makes sense.
Yeah, thank you.
Cool. Other questions? I have a question while people are thinking of some. So you have this sort of like double loop strategy for computing an approximate resolvent. I would imagine you would need to know some parameter for the inner loop, or is there also a
nice
for the inner loop?
Excellent. So yeah, the inner loop, the way it is done here is by using a variant of Extragradient. And normally for Extragradient, you would need to know the parameters, but here when you are adding the resolvent, you know the strong convexity parameter. You're adding this term just with constant 1. And so strong monotonicity parameter is already known. And there is a way to make the whole thing work without knowing the Lipschitz parameter, just by using this backtracking or doubling trick.
Oh, okay. I'm familiar with that, yeah.
Yeah.
Okay, cool. Adrian.
Yeah, thanks, Jelena. So the hypermonotone case, do you kind of see that? Do you see that in practice, or I mean, or does that arise kind of artificially by kind of regularizing somehow?
Oh, good question. I don't know enough about what happens in practice. So I know, like, when I looked at these papers, that people had some type of examples where they saw them arise in practice. So the whole reason they came up with is they were just applying proximal point methods, and they saw, the method converged.
Right.
We had this one example from this von Neumann ratio game, which is actually constrained, and our results are from unconstrained, but there's a way to generalize them. Let's not get into those details. But there, not every one of them would satisfy this condition, but some of them will satisfy that condition and not any of the special cases. So at least it gives you kind of a better explanation why things can still work.
I mean, you kind of see it in ordinary optimization. You kind of see it from kind of doing proximal point and then kind of increasing the parameter because of the non-convexity somehow. And I just wonder whether you ever see the same kind of phenomenon with the variational inequality setting.
Yeah, not yet. I to be honest, I was only doing theoretical work on this side, so I
was just curious.
Yeah, it's a good question. I think.
Okay, well, if no further questions, let's thank Jelena again. Let me. Thanks so much for coming to give us a talk. Really appreciate it.
Thank you very much. I've had a great time so far. So yeah, I look forward to the remaining meetings.
Sounds good. All right. See you later.